Hello everyone, this is NK, and in this video I'm going to make a presentation on the paper Vision Transformers. I'll mainly focus on the model architecture, but we're also going to go through a brief overview on the introduction and abstract of this paper, and also talk about the results from the model performance. So the Vision Transformer, as we see here, applies transformer architecture to image classification. In a previous video, we had talked about how transformers were used for NLP tasks, that's text cases, but for this paper, the transformer is applied on images. And for that to happen, the images are broken down into fixed patches, linearly embedded, positional embeddings being added, and then these are fed into the transformer architecture. And we can see here, you have a whole image, which is broken down into patches, and these individual patches are then passed on to the model. And for this to work, this requires large-scale pre-training but achieves state-of-the-art results. So if we take a brief overview of the architecture, the first thing we'll notice is input images are being split into patches, in this case 16 by 16. So we can see the input image here, which is being split into patches and then past the individual patches 16 by 16 sizes. But the images are not passed as they are in our 2D shape, because remember we said the transformer was built for text cases, which are 1D input formats. And so to transform these 2Ds into 1D formats, they are first flattened and then projected linearly to form patch embeddings, as we can see over here at this point of the architecture. But before adding positional embeddings to this, a learnable class token is also prepended for classification purposes, and then positional embeddings are added to retain spatial information, as we can see at this point of the architecture. And going through the process, we see that these patches and positional embeddings are then fed to the transformer encoder, which passes the results or the output from this to a multi-head perceptron, which then is used for classification. And taking a deeper look into the encoder, this is a standard transformer which processes sequence of embeddings. And as you can see on the right here, we have the embedded patches which have already been flattened and passed as input to the encoder. They go through a normalization layer first, then multi-head attention, and you can see the residual connection over here, and the output from that is passed to another normalization layer and then to a multi-layer perceptron. And over here we have another image which kind of summarizes the whole process, and we can look at some of the key components. The first thing we see is the patch embeddings, where image patches are being converted into tokens, as we can see in this step over here. And then we have positional encoding, which provides spatial structure, and that input is being sent to the transformer encoder, which is comprised of multi-head, self-attention, and feed-forward layers. And then that is being passed to the multi-layer perceptron for classification. And you can see all of these steps in the image over here. And taking a brief look at the results from the transformer model, the Vision Transformer matches or surpasses state-of-the-art CNNs when trained on large datasets, for example the GFT with 300 million images. And the winning formula is pre-training on large datasets and then fine-tuning on smaller datasets to yield stronger performance. However, without sufficient data, VIT models usually underperform compared to CNNs. And looking at the table, we can see a little bit of it here. You have some of the Vision Transformers over here and previous benchmarks over here. This is compared to the ResNet and EfficientNet. And we have some variants of the Vision Transformer here, a very light variant here, a larger model, and a huge model over here. And these 14, 16, and 60 here are just the size of the patches. And based on this large Vision Transformer, which was trained on the GFT 300 million with 300 million images, has the best performance on the ImageNet dataset, ImageNet Real, CIFAR 10, CIFAR 100, and so all of these models, it has the best performance. And you can see here the comparing the efficiency, it has also a very good score compared to the previous benchmarks, ResNet and EfficientNet. comparing you have from 9,000 TPU core days going down to 2,500 TPU core days and even 0.6,000 TPU core days. So in conclusion, this paper demonstrated that transformers can outperform CNNs in vision tasks with enough data. The vision transformer introduced patch-based image tokenization approach, and it also highlighted the importance of scale in model performance. That's for models to perform very well, you just need a lot of data and then you can fine-tune on a specific task. And this paved the way for subsequent transformer-based vision architectures. Thank you for following up with me up to the end of this video.